I think okay. Now it is better. You can hear me. Yeah. So we can go ahead. So we have already reached five. So we can start now. So before that, if you have any more other questions or something not understood so far, you can speak now. You can unmute yourself and so right. So this is your week 3, and uh, so we'll be discussing some problems or some topics particularly related to quantum statistics. So far you have seen till your week 2. So the topics that have been discussed, so which is already there uploaded on your NPTEL portal, you would find like many discussions related to the I mean various ideas of statistical mechanics, particularly concerning to to the distribution of particles or whatever atoms or molecules which you have been discussing them in a classical idea or in the classical notion where uh, uh, I mean the laws of thermodynamics that we have seen there, or the laws of statistics that we have seen, they somehow obey some classical laws, and based on that, we have found how I mean that how your statistical behavior, how your probabilistic and statistical analysis gives rise to various thermodynamic properties and so on. So you have seen them till your like week 2, or maybe in some topics in week 3. But now you can see like what happens when you consider the particles that you are dealing in this statistical analysis to be some quantum mechanical. Like those particles are not classical anymore. So because when you talk about particles, like when you particularly talk about fundamental particles like something electrons or photons, so they are quantum particles. So and their dynamics and their uh, they pertain to very different like dynamical laws, which are essentially explained through quantum mechanics. And I hope you have seen quantum mechanics, or you have gone through quantum mechanics before in your undergraduate level. So we just need some basic idea of it, and that's it. And we'll see more about other quantum features in this uh, discussion, or the problems that we'll be discussing. So yeah, so one major thing that you will have to specify yourself when you talk about quantum statistics, that the particles that you will be dealing, so they will be they so they will be essentially identical, and they are indistinguishable. So, like you you've seen in when you were talking about classical statistics, so those particles were something distinguishable, but here they you will consider all of them as identical and indistinguishable. And um, so in quantum statistics, there are two possibilities, or basically you can classify your quantum statistics into two broad categories. So one is Bose-Einstein statistics, and the other is Fermi-Dirac statistics. So the other is so like so what specially happens in these statistics? So first, if you see both Einstein statistics, they are obeyed by some particular set of particles, some particular kind of particles, like which has uh, particular kind of quantum particles which has the integral spin. meaning quantum particles, all quantum particles has some spin to them. I mean, that is an intrinsic property of every quantum particle. Whenever you talk about any quantum particle, whether it's a proton, neutron, or like photon, any fundamental particle, any quark, leptons, whatever you know about quantum particles, so they have some spins. So there are some quantum particles which has integral spins. Like if you see their spin value would be some like integral value of h bar. So if h bar is, let's say, is the unit which you are quantifying the spin. So n is some number which is like I mean some integer which is one, which goes like as one, two, three, or also zero. So so uh, uh, like for example, photon, like which has a spin one, like uh, and uh, um, uh, and there are other like I mean like fundamental particles. Like if you think of, like there are something, or you have heard of, like Higgs boson. So Higgs boson also like uh, its spin is also like has a spin value of zero. And yeah, so there are some other gluons, gluon particles. Maybe most of these particles you would be unfamiliar with them. Maybe you can like come across uh, in some higher topics or some advanced topics when you will go, particularly when you go and read particle physics. Or if you have seen them, you can already realize it. So these are the particles which we know them as bosons. They if they follow if they have this kind of integral spin, like we just name them as bosons. So photon is one of the familiar one which you know, and you will see that, like I mean this uh, and this like bosons, like if you see uh, they obey I mean they are quantum particles. So every quantum particle you can uh, represent them by some wave function, some wave function side. So you can see that, like for bosons, they have a particularly a feature in their wave function. When you denote a boson by a wave function like psi, it will be symmetric. So it could be something uh, if you talk about in position. So this wave functions would be symmetric. So which means, like they obey some kind of mathematically they would have this uh, nature of so it's like how you would represent a symmetric function. So that is how this wave functions also behave, particularly if they are bosons. So now, but in statistics, what really matters here is, so you would come across this expression quite a lot of time, and this is what going to be the again one of your elementary things when you talk about your Bose statistics, which you would be using this over and over to calculate various properties which obeys Bose-Einstein statistics, and so. Uh, so I it's outside. Sorry for that. So yeah, I was talking about this. Um, you, I mean, this is your expression. So this says that, or basically, uh, this tells about the probability of uh, bosons in your system uh, occupying uh, uh, occupying energy epsilon I. So if you have a some system, let's say uh, in uh, in some volume, you have some particles which are all of integral spins, means they are bosons. Then uh, if you want to find some particles with energy epsilon ei, then number of particles or the fraction of particles that you will find with having energy ei will be given by this function. So this tells you about the fraction of particles, the probability of particles, particularly bosons here, that you can find with energy ei. And um, yeah, right. So and yeah, you can this expression would have been derived in your lectures. You can see that in more detail. And then something more uh, yeah, now if we talk about Fermi-Dirac statistics. So again, these are mm, so 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 these are applicable for particles having uh, half integral spin, uh, and further, as we so they have anti symmetry, anti-symmetrical wave function. Uh, yeah. So again, so here you can say that these are again there are certain fundamental particles, and so here some bosons, examples you can say photons, or there is something you probably know, Higgs bosons. Um, so these particles have spin some integer of uh, h bar, uh, and for Fermi-Dirac, you can have uh, electrons, uh, you can also have protons, and, yeah, there are quarks. So these particles, they have spin something, uh, uh, we can get it like this, meaning they have half integral spins, like uh, uh, for electron or proton, the spins are like half times h bar. So h bar is the unit which you can quantify the spin. So then uh, so it can either have some plus h bar by 2 or minus h bar by 2 state. So I guess you have already seen that if you have gone through quantum mechanics course. So before this statistical mechanics. So I guess like this level of quantum mechanics, no, I mean, at least this is very like basic level of quantum mechanical, I mean, knowledge. So you have done probably in your first semester. So yeah, so these are such particles whose statistics will follow slightly different uh, behavior, and they have different other additional features. So we can go through them. And further, as we were talking about this particles are quantum, and if we talk about this fermions, so these are known as fermions. These are here known as fermions. So for this fermions, if you represent a fermion by a quantum mechanical wave function, they are quantum particles, then you will find that they obey this feature, that is, they are anti-symmetric. So their wave functions are anti-symmetric. And likewise, you also have a probability function, or otherwise, this is, you can say that this is um, uh, bosonic distribution. Like here, in this case, we can say this is a bosonic distribution, and here we have a fermionic distribution. So again, this is very similar. You will have uh, Zi, and so So then here in this distribution, like again, uh, I mean, you will see that these two distributions are very similar. There's just a difference in sign in the denominator. Here you will see that like there is a positive sign here, but here a negative sign makes this is a bosonic distribution. Otherwise, this is a, fermionic distribution. So uh, and this gi epsilon I, these are your as we have discussed them before also. So so this gi uh, is your degeneracy of energy, or of energy ei state, and alpha and beta are some constants. So alpha, beta, uh, like if you see basically this uh, alpha, beta, are basically uh, maybe I can uh, this alpha is given as uh, beta epsilon I, and not epsilon I over kbt, and beta is here uh, uh, now probably I'm doing a mistake here, so let me write down. uh, okay, so this uh, to know exactly what alpha and beta, so you can just compare it with the actual expression. So, suppose I'm writing this for Bose-Einstein. So this will be basically equal to Zi epsilon I minus epsilon f over kT. So this epsilon f is your Fermi energy level. So that means like at zero temperature, if you keep your system, your uh, thermodynamic system consisting of these particles, like at zero temperature, they will fill some energy state up to some energy state. So that energy will be your Fermi energy level. Yeah. So probably uh, you can quickly see example. Consider two different systems, each with uh, three identical non-interacting particles, and both have uh, single particle states with energies epsilon naught, 3 epsilon naught, and 5 epsilon naught. So epsilon naught is some positive energy level, some positive energy value. Then uh, let's say one system is populated by spin-half fermions, uh, and the other by uh, bosons. So now, uh, so these are two different systems you have. Now calculate uh, uh, EF minus EB, where EF is the ground state energy, uh, of fermionic system, means the system filled by spin-off particle, and EB is the ground state energy of bosonic system. So here it is clearly given to you that your system has three energy levels, and they are filled by like One, they are filled by uh, fermions having spin half, uh, and there are three identical non-interacting particles. So that means there are three fermions which are filling epsilon naught, 3 epsilon naught, and 5 epsilon naught system. So that is, let's say, uh, if I say that, let's first consider fermionic system. So they have spin half. They are spin half. So for a given spin s, the total number of fermions that can fill an energy level is given by 2s plus half uh, fills a given energy level. So, if s is equals to half, then um, then two fermions fills a given energy level. So maximum you can have two fermions in a given energy state. So um, yeah. So if this is your energy level epsilon naught, and you have another energy level 2 epsilon, and then the third energy level which is 3 epsilon. So um, since so this is um, and one more thing, that like this degenerates, I mean, this 2s plus 1 condition that tells that this number of fermions can fill the uh, I mean, given energy state. So that is because of Pauli exclusion principle. So this comes from, so this tells that no two quantum particles can fill a given energy state having the same quantum numbers. So when I talk about s equals to half, so like that means s equals to half particle can have two distinct can have two different quantum state. So like for example, electron has two distinct states. So one, it can have a spin half state, and it can have the other oppositely spinning state, that is the spin negative, spin minus half. So these are two distinct states. So you can fill, let's say your fermions are electrons, then you can fill two electrons at maximum. I mean, any given energy level. So these two are not these two. Let's say I have one fermion denoting as some arrow with denoting some positive spin, and another fermion or another electron having the opposite spin. So these two are, since they have opposite spins, opposite quantum states, or basically they are different quantum states, I can fill them. And now I cannot fill any other fermion. So because if I have to fill any other electron here, that would be again something opposite, or could be yeah, again it could be upstate electron, or it could be either downstate electron. But I cannot do that because I have already filled one of these state in this ground state. So that is why I can have only maximum two electrons here. So we have a total of three fermions. So two we have filled it in the ground state, and no more we can do it in the ground state. So we have to go to the ground state means the lowest energy level here, that is the epsilon naught. And then the uh, since we cannot fill any more in the epsilon naught, we have to go to the 2 epsilon, so there will fill another node. So we have total of uh, 3 fermions. So that is the lowest possible. That is the lowest possible configuration. Or that is the only possible configuration that you have for 3 fermions that you can distribute in these 3 energy level, attaining low energy configuration, lowest energy configuration. Because uh, if I would have instead of filling the last fermion into epsilon, if I fill it at 3 epsilon, then this would have been not mm, lowest energy, because we need to calculate uh, EF minus EB. So where EF is your ground state. So, if we want a ground state distribution, which means lowest energy distribution, then you cannot fill this last fermion here. So, you have to fill it here. And also, I could have done this, uh, but you will again see this will give you more energy. So this will be epsilon naught, 2 epsilon, 3 epsilon. So that is total of 6 epsilon naught. But the earlier configuration, this had total of 3 epsilon naught. So, this is the only possible configuration with lowest energy. So only configuration or only distribution with lowest energy configuration. Okay. So your EF becomes twice of epsilon naught plus 2 epsilon, that is 4 epsilon. Sorry, uh, like I think initially it said if energy levels are epsilon naught, 3 epsilon and 5 epsilon. So yeah, I just wrote them epsilon 2 epsilon here. Let me. So these are epsilon naught, 3 epsilon naught, 5 epsilon naught. Okay, so that means this will be 3 epsilon. This is 5 epsilon. Now, if you do this for bosonic system, so in bosonic system, again, you can have these energy levels, that is epsilon naught, 3 epsilon naught, and 5 epsilon naught state. So for bosons, there are no such constraints like Pauli exclusion principle. So there is no Pauli exclusion principle. So any number of particles or basically bosons uh, can be filled in a given energy state. So uh, so you have three bosons. So for a distribution corresponding to lowest energy configuration, because I want a ground state for this bosonic system, then I have three bosons. I can fill them all the three here in the lowest energy level, that is epsilon naught. So that will give me a total energy equal to 3 epsilon. So uh, yeah, I cannot fill one of them if I take like from here to here, then that will give me 4 epsilon naught. So that will not be a ground state. And yeah, same, I cannot uh, put one of the bosons here. That will again correspond to some higher energy configuration. But I want the lowest energy configuration, which is the ground state. So that will be the case if I put all these bosons in the ground state, or I mean in the epsilon naught state. So that will give me the lowest energy possible configuration. That is the epsilon. So now, as it is asked in the problem, that we have to estimate what is the difference in the ground state energies of these two systems uh, between fermionic and bosonic system. So that will be um, 5 epsilon naught minus 3 epsilon naught. Yeah. So this is just a very uh, basic idea about how fermions and bosons, like they I mean they have a distribution across different energy levels, and they are indistinguishable particles, so their distribution will be different than the one which we familiar with in classical distribution. Okay. Um, okay. So now uh, we can discuss a bit more on this Bose-Einstein. So we can go with this problem. Uh, We can see one more quick example here regarding your bosons and fermions. So suppose um, uh, so there is a phenomena that is very popular in case of bosons. So when you talk about bosonic particles, so at a certain given condition, so they will exhibit a phenomenon known as Bose-Einstein condensation. So we'll just discuss in shortly. So so uh, so these are so so it will be seen for bosons. Um, so so suppose if I for which of the following case the uh, phenomenon of B condensation means the Bose-Einstein condensation will be uh, can be found. So that is, let's say, uh, hydrogen. So yeah, again, you remember this B condensation. It is seen for only bosons, and bosons you have integral spin, and if if they are not integral spin, like something like if they are half integral spin, then they are fermions, and the fermions do not show this Bose-Einstein condensation. So that is what you have to figure out if in this hydrogen atom whether you can see Bose-Einstein condensation. So let's say if in hydrogen, the if we talk about number of protons in hydrogen, uh, so in hydrogen you have let's say a given atom X um, will have uh, 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 some number of protons, some number of neutrons, and some number of electrons, and each of them has a spin half. So proton has spin half, and also electron and neutron as well. So all of them have spin half. So if I take hydrogen, then uh, uh, so for hydrogen, number of neutrons will be 1, number of electrons will also be 1. So I have total uh, particles, uh, that is, uh, I mean, mm, uh, these are basically, all of these are, remember, all of these are, or uh, these three are fermions. But if you take this atom, this atom hydrogen right here, since it has one electron, sorry, yeah, one electron, and also one neutron. So the total spin that it can have. So if I take the total spin, it can either have 0 or 1 or minus 1. So, and you will see that, uh, the um, what I mean to say, the total um, the total number of I mean uh, the fermions that you have will be something 2. So you have the total number is 2. Uh, let's say n equal to, so you have one electron, one neutron, equal to 2. But yeah, as I was telling, so each of them are fermion. They have integral spin, but if you combine them, their combined spin would be some integral value of spin. So it will be not be, it will not be like 1 by 2, 3 by 2 spin value anymore, because if you take the combined spin, it will be either, it will be some integral spin. So if they have spin half, so it can have spin 0 or spin 1. So that is why. So if you have n, the total number of fermions in your atom is something even, then your atom X will behave as bosons. So that means your H1 will show uh, Bose-Einstein condensation. Then you can see the uh, yeah. So this is your case of hydrogen. Uh, then you can also see these for helium. So in helium also you will find number of neutrons in helium will be 4, and number of electrons in helium uh, will be 2. So again, if you take the total sum, it will be 4 plus 2 is 6, is even. So this will again show, so your atom X um, will be a boson if n is even. That means your helium 2 will also show uh, the condensation. Again, if you see like case 3, that is, let's say, uh, sodium Na1126. So here also you will find uh, so So this basically N means this is your total content of nucleus, not just neutrons. It also includes protons. So I I probably would have said only neutrons, but it means nucleons, number of nucleons. So in helium you have total of four nucleons, like two proton, two neutron, and so here you have only one proton in case of hydrogen. So it's only, yeah, one nucleus. So yeah, in sodium also you have 23 and 11. So total number of nucleons in sodium, that is 23, and yeah, and your electrons would be 11. That means your total is again something even. So this will also show Bose-Einstein condensation. Now, for case like, let's say, uh, this potassium. So here you will find that I mean your number of nucleons is 40, but your number of electrons is 19. So your total, that is 59. So it's odd. Then uh, this will not show will not show B condensation. Yeah. So that is uh, so yeah, that is some more bit of information, like when exactly you can have a system of bosons. So when you are considering these atoms, so these atoms can behave as bosons or they can behave as fermions, like depending upon the total spin that each of this particle or each of the atom uh, like I mean like whatever would be the net value of their spin. So that will decide the type of distribution that these atoms or particles that they will uh, take in your system. So as I said, like I mean fermions are only of half integral spin and bosons are of only integral spin. So, but in this example, you found that I mean these atoms, although they are made of fermions, but they integral spin. If you look into each of the given atom, they again have some integral spin configuration. That is the I mean the net spin of the given atom. So overall, if you consider that atom, a collection of that atom, and if that forms some thermodynamic system, then the statistics that they will obey will be some Bose-Einstein statistic type. They will always some Bose-Einstein type statistics and can also show Bose-Einstein condensation phenomena. So yeah. So now we can see what is this Bose-Einstein condensation further. So if you have any questions till now, or anything that is not clear, you can ask. Uh, okay. So uh, so here in this problem you have some n spinless Bose particles. So spinless means spin having zero, and each of them has some mass m, and it is enclosed in a volume v and at a temperature t. So, so first thing you have to find out an expression of d of E, that is your density of states. So density of states, basically it refers to, so uh, so it basically tells like number of uh, uh, um, number of energy levels in uh, in energy in a small energy unit. Uh, some epsilon uh, in epsilon and epsilon plus del epsilon. So in small d energy like uh, unit, like how many energy levels, how many energy states can be filled in, or like how many energy states are available within this d energy range. So uh, for uh, so uh, so now to get an expression of this density of states, so what we can do here is uh, so we know the phase space volume, uh, we know the uh, so let's say that I mean the Bose particles, like these are it is given to be like non-relativistic. So non-relativistic means like they are not really in relativistic regime, which means that their dynamics are not so much that they're uh, I mean they are traveling with very high velocity close to c or something. Yeah. So if that is the case, then we can uh, so so in that case we can say that for non-relativistic, this we know, yeah, we know the energy is given as p square over 2m. So and since we know this energy and momentum relation, so suppose if we can calculate something, how much number of so if we can measure number of momentum levels or momentum levels between E and P plus dp, then we can also say that like how much energy levels can also be there between E and E plus d, like from this particular relation. So the reason I said like it's we can just like not relativistic, so we can start with the simple relation between energy and momentum. So if it would be relativistic, then you could have taken the usual relativistic relation, which is like something from like a square root of p square c square and then some m square c to the power 4, some other terms will be there. So that is another like a bit more a bigger relation. But here, yeah, you just have a straightforward relation between energy and momentum. So but to get how would you measure the number of momentum levels between p and dp? So you know in so so this is something at the starting you have learned this like in your first week, that your phase space volume like is something given as, let's say, this is this denotes something your phase space volume. So that is your d cube x and d cube p. And so suppose if I integrate it over your space, that means your volume, then you have something. Um, uh, if I integrate this over space, then you have and you would have also seen that it also has a 1 over h by h cube normalizing. So this is a factor that so this is your elementary volume. So this is your elementary phase space volume. So from here you can determine what will be your number of momentum levels between p and dp, p and p plus dp. So so now you can have so if you integrate this over, so there is 1 over h cube. uh, so once you integrate this over volume, so you will have something v over h cube and d cube p, and this d cube p you can also uh, yeah, so you have d cube p. So you've integrated out this volume. Then further you can also integrate out the so your d cube p basically means uh, so it basically means your dpx, dpy, and dpz. Or otherwise I can also write in polar coordinate, it will be something like your pr square sine theta, then dpr, dp theta, and then dp phi, something like that. So if I integrate out only the surface part, so suppose I mean in polar coordinates, if I write down only in terms of uh, dp. So let's say I am integrating out the surface part. So I'm denoting that surface by some sigma. This means your phase space surface only covering the momentum. So this is your momentum phase space of the phase space surface. So so this will be something like um, p r square sine theta, p r square sine theta. So or let me just p, then uh, then you have something so dp theta and dp phi. So so that will just give you something 4 pi. So these are things that you have seen already. 4 pi p square. Yeah, 4 pi p. Let me, 4 pi v over h cube. Uh, so p square dp. So this will be your um, uh, yeah. So this will be your number of momentum levels in P and P plus P2. So, so this so now using this relation that we have for this non-reducing case, like your relation of energy and momentum. So you can write it as something uh, equal to so so you have something dE equals to uh, or rather Yeah, d equals to p over m dp, and so m d epsilon is p dp, and if I multiply root p on both the sides, and p is here basically um, square root 2m e, so 2m dp is here p square dp. So using this you will have uh, so so from here I can write it as 2 pi v over h cube 2m 3 by 2 epsilon 1 by 2 uh, and d epsilon, so or d whatever. So now I can call this as my density of state. So that is the number of energy levels in with energy levels in epsilon and epsilon plus d epsilon. So that is what your energy, that is what your density of state is. So that is 2 pi v over h cube 2m 3 by 2 epsilon half. Okay, so then the next thing you have to find out here is what will be your Bose-Einstein transition temperature. So what is this Bose-Einstein temperature yeah. So before that, like we can see, uh, let's say that uh, uh, use uh, n prime epsilon is so this is again the this is the probability function or the distribution function for the Bose-Einstein statistics, which is given as something epsilon e minus mu over kt. So the Fermi energy which I was denoting earlier, so that is, let's say it is given as mu over kt. Uh, Mu is your chemical potential, so this is minus one. So this is your usual Bose-Einstein distribution. So using this, you can find out like what will be your uh, Bose-Einstein transition temperature. Um, so what happens here? So let's find out the total number of particles or total number of so this is number B. So the total number of bosons occupying uh, uh, let's say so this so we have this distribution which I just wrote it in the question. So that is given to you. So that is what we have been discussing from the beginning. So your so this is your given probability function or distribution. So I'm writing down here again. So make sure that this is only valid if mu is less than or equal to 0. So this is bit essential. So you can see if mu is not, or if mu equal to or greater than 0, then that means your n epsilon is negative. So this is not physical. So this is not physical. I mean, you cannot have some negative probability distribution, negative like average or something. So this is you have a very fine condition here that your mu should be less than or it can be also equal to 0. So that is when mu is 0, that is what something we will see like what exactly happens there. So that is where something we'll find some transition temperature which we are calling, or it is given in the question to be some Bose-Einstein temperature. So yeah, one important condition here is that mu should be less than or equal to 0. Then so what we can do here, so we can calculate. So this tells the, as we have discussed at the beginning, at the start of our today's session, we said that this is your probability of finding uh, your finding bosons with energy epsilon. So if I want to know what is the total number of bosons in the system, so what I can do, I can integrate this entire this n over all different energies. So what I'm saying, to know what is the total number of bosons, so I can take uh, n epsilon with and also I have to use the density of states. So density of states is I calculated above, and if I integrate this over all the epsilon, then I will get the total number of bosons. Total number of bosons. So yeah, so like I can calculate this total number of bosons. Let's say this density of states, which um, yeah, you use the density of state expression that which we just calculated before in this, yeah, here, uh, and using that plus I mean again you will also have to use this probability function in order to get the total number of bosons. So that is the definition of to calculate your total number of bosons. So this is a user statistics, how you do it. So so if I put all these things into this value, so I have to integrate this over all the available energies. So then it can give me the total number of bosons, because your all the bosons that you have in your system can be having any energies ranging from 0 to infinite. So then upon using the density of states relation and also the probability distribution for the Bose-Einstein, you will have 2 pi over 2m 3 over 2. Then you also have something volume, 2 pi h whole cube. So then you integrate this out from 0 to infinite. Then you also have some epsilon half which you will be integrating. Then uh, uh, exponential epsilon minus mu over kbt minus 1. Now Yeah. So this gives you um, total number of fermions in your or bosons in your system. Now, if you want to know what is the number density of your system, then like the number density of bosons can be just calculated from here. That is just n over b. If you just divide b on both the sides of the above equation, so you just have 2 pi over h cube 2m kt 3 over 2, and you integrate this again from 0 to infinity. I'm just introducing, so this will happen after I introduce a variable which is x. So then that is dx x minus x mu minus 1. So your x is basically epsilon over kt, which is integrating now, and your x mu is your constant, which we said it is related to your Fermi energy. So here we are denoting as mu by kt. So yeah, again, as we have said, so since mu should be less than equal to 0, that means your uh, x mu should also be less than equal to 0. Then so now what happens, so we have to find out what is we need to find we need to find critical temperature Tc. So since you can see we have a condition that mu should be less than equal to 0, or let's say I have some temperature T, which is given through this x mu or x, which is the new variable which we have introduced here. So the temperature is now related with x here. So so what happens if I decrease the temperature? If we decrease temperature T, then uh, then mu will increase. So why this will happen? You can see here. So okay. So when I am decreasing this temperature, um, um, so this x is related with this temperature. So that means your x is increasing. So you can see when I decrease temperature of the system, then your x will increase, and also here in the uh, uh, let me just clarify this. Mm, just give me a moment. Okay, so as I was talking here, I mean, I was talking about temperature. If temperature decreases, you can see there is a prefactor here. So this prefactor will decrease. So if this prefactor decrease, then you have like one thing you should note here, that this n by v is fixed. So your the system has fixed n by v, means you have fixed number of bosons and the volume is fixed, they are not changing. So so if uh, uh, t decreases, then you also have something, the prefactor that which has t over 3 by 2, so that also decreases. So and in that case, if your prefactor decreases, then your integral value should increase. So that means your integral, the the integral should increase to maintain or to preserve uh, constant n by v. So and that will only increase if you see that when mu will increase, this will happen only if mu increases. So so that is why uh, in this case, if you decrease the temperature, mu will increase. And yeah, so like it is like if your mu is increasing, then your exponential will become smaller and smaller, and let's say your it will become like something like your exponential to the power something, your mu cannot be negative, so that is which we have sorry, your mu cannot be positive, that which we have made it clear. And further, as we are saying that mu needs to increase, it means it needs to increase from negative towards zero. So uh, so as your mu, if your mu will increase, your then your exponential will become like you can see that it is becoming more smaller, and your denominator will be again something will be smaller, and the overall integrand is bigger, so it is increasing. So that is what we need to ensure. So that is why uh, here when you decrease the temperature, your mu will increase. So then but yeah, so now we are coming to the point where we need to find out uh, so what is your Bose-Einstein transition temperature. So yeah, okay, uh, just a minute. Okay, there's some technical error. Okay, yeah. So yeah, I was talking about the critical temperature. Now, so here mu will increase and approach zero. Uh, if uh, Tc is the critical temperature, then uh, so it is like, let's say you are at some high temperature and you are going towards a temperature, you're decreasing the temperature and you hit a temperature that is Tc. So that as you are lowering the temperature, so then when you arrive at this critical temperature which is Tc, so then T equal to Tc, you will have mu approaching towards zero. So and so that is what again uh, in order to keep n by v fixed, so that is what we have been trying to do. So so then the particle number, uh, like so let me write down the so your n is your uh, number density. So for that is given as 2 pi over h cube, 2m 3 over 2, uh, 0 to infinite epsilon half del epsilon uh, over exponential epsilon over kt minus 1. So so at n t equals to tc, you will have 2 pi over h cube, 2m ktc, 3 over 2, uh, 0 to infinite uh, x half. So you can see like we have mm, so we have put mu equals to 0 here, so that is why you have only epsilon by kt. So you have to put epsilon minus mu over kt or kbt. So this or otherwise maybe I can write it here. Um, so this implies epsilon sorry, exponential epsilon minus mu over kbt will go exponential epsilon over kbt. Then you just have to integrate this. So that is x half dx dx minus 1. So there is a like, I mean, let's say this integral value. So this is just a number. This is also given to you. So we will not get into how the integral comes. So integral value is just a number. So that is just something which you can find it or calculate in any computer as well. So let's say that integral uh, also use the integral value 0 to infinite x, this is square root x over exponential x minus 1 dx, and something, the value will come out to be 1.3 06 square root pi. Yeah, so that is what, that is you will get. So use that. So using that value, so yeah, so once you will use that, so you will using the given value of integral, so you will get your critical temperature, something is h squared over this is, yeah, kb kb 2m kb, then n over 2 pi a is your integral value 2 by 3. So a is your integral value. So this is what your critical temperature will look like. So that will depend on your number density. Uh, yeah, if there is any question or something, you can ask. Okay, so then next we need to see what happens across this critical temperature. What will happen to mu and your average number density and your internal energy. So when t less than or equal to Tc, your mu is almost around zero. So your mu again, as we just discussed, your mu cannot be greater than zero. So otherwise your probability function itself will become negative, which is unphysical. So then that means your uh, let's say, I mean, for number density um, corresponding to uh, since your mu is still going to remain zero, That means your again the factor which you get in the um, in your probability distribution for Bose-Einstein distribution, where you have something epsilon minus mu over kVt. So that will be also equal to exponential epsilon over kVt. So then that tells that, and then so yeah. Uh, so that means your number density, or yeah, your what you can say, the probability density for, let's say, for epsilon greater than 0, you have 1 over, this is your probability function, will be something epsilon over kVt minus 1. And uh, and for epsilon equals to 0, which means your lowest energy state, for that, uh, what you can do, uh, for uh, lowest energy state, you can uh, take your total number density which we have calculated, then you subtract the um, uh, then you subtract the total number occupying the positive energy state. So that will give you occupying the E greater than 0 state. So that will give you n bar epsilon greater than 0. Again, you do have to do this density of state things, and yeah. So if you do this like the same exercise which we have done earlier, so this earlier we have taken it to be something um, for generic E. So now you have to consider for epsilon greater than 0 at so we are doing, remember, at this place where t is less than or equal to 0. So uh, if you do this like the same exercise which we did it right here, um, yeah, for the case when we evaluated the total number of n. So the here we consider, let's say, this was uh, your probability distribution. The same you have to do here. Once you do that, like you have something like you can take n common outside and you put everything in their places. All the expressions already we have seen, we have I mean given here. So just put it in their places, and again you have a similar integral, that is x square root dx exponential x minus 1. And again, you know, this is some value of integral which we just taken it to be some constant value, that is a. So then the important point here is you will find something n, I mean this expression will turn out to be of this form. So 3 by 2. So now the point here is, you can see when this yeah, 1 over p pc 3 by 2. So this tells you that total, or the uh, fraction of bosons uh, in the ground state, that is epsilon equal to 0. So generally we know, like for a um, uh, for a given n bar e, which is given by the usual Bose distribution. So here in this case, for epsilon 0, this is the condition, and we know that. So here epsilon minus mu over kt minus 1. So here we have for the case for epsilon particularly equal to 0, the fraction of. So this is for any given e, and here epsilon is 0. So for epsilon equal to 0, this is your condition. So what it is, let's say, as we were talking about the temperature, when we are at some temperature which is T, uh, let's say T greater than Tc. So at T greater than Tc, uh, what you have, I think mm, uh, the okay, let's say at T uh, equal to Tc, what happens? Your uh, this fraction of bosons occupying your energy state, occupying your ground state energy will be 0. So that means your uh, at critical temperature you will have almost 0 number of bosons occupying your ground state. But once when you go T less than Tc, like uh, um, once you go like T less than Tc, or you will find your n epsilon 0 will have something greater than 0, which means till critical temperature you do not have, I mean, at critical temperature you do not have anything in your ground state. The fraction of bosons is 0, but you will have some fraction of bosons occupying your ground state when your temperature drops below critical temperature. Now you will see, surprisingly, when you go to like temperature when uh, even smaller temperature, like close to at 0 temperature, you will find all the bosons uh, will be occupying, all the bosons of your system will be occupying your ground state at t equals to 0. So that means this is you find very I mean, um, um, at absolute 0 you will find all the bosons occupying the lowest energy level. So this is not something which you see in fermions in or in any other places, like I mean at even at t equals to 0, like you see the particles fill up to Fermi level, but here in particularly for bosonic systems, you this see this special behavior. All the system like comes to the lowest most energy state. So this is what something known as Bose-Einstein condensation. So this is the popular Bose-Einstein condensation. So due to this feature, you have some like very like I mean very I mean amazing experimental outcomes which are also done in the labs. So like some kind of helium superfluids, which you see that those fluids have a very extraordinary property of having zero viscosity, So all these things that comes due to this mechanism of or the principles of this bosonic Einsteins that you are seeing right here. So yeah, and so again, like at t less than tc, so there was one more point there, like what would be what happened to internal energy. So internal energy you will see. So again at t less than tc, you have internal energy. You will find. So again, uh, we will use the similar uh, energy um, and again you will evaluate the similar thing. So, but remember, we are doing this at uh, t less than tc. So, so again, you have something. You have to do the similar integral once again. 2m over 3 by 2 kt over 5 by 2. Then again, this will be 0 to infinite uh, x 3 by 2 dx e to the power x minus 1. Then this will be something equal to 0.77 n kVt. So this case, all these cases are kV, so your Boltzmann constant. So like don't get confused if B is missing in the subscript. So yeah, so that is what your internal energy. Okay, so probably like we may not have another example to discuss more on the Fermi statistics Fermi-Dirac. Maybe we can see next time. So likewise, there are some other very interesting properties or mechanism in fermionic theory as well. So there also you see some kind of a very I mean due to Fermi statistics, you have a distinct Fermi pressure and Fermi energy, and due to the that conditions of Pauli exclusion principle, you'll see that even in ground state, I mean the quantum particles, the fermions, will not occupy the lowest energy state that you see in the I mean uh, Bose-Einstein statistics, or in case of boson, we found like once you are crossing the critical temperature, once you are going below the critical temperature, you'll find all your bosons coming to your like I mean your E equals to 0 level, and once that is filled, you get a different type of metal. Like so, that is the artifact or manifestation of this bosonic mechanism, bosonic principles. That is like that is the underlying the underlying principle of bosons, which can um, lead to this kind of like very unique outcomes. And further, like as I was talking about fermions, like there you will have some Fermi energy level even at T equals to 0 temperature, and then there is, due to that Fermi energy level, you have some Fermi pressure. So even so, like for example, there are things like if you have um, known about, or you have come across, or ever, maybe probably somewhere you've heard of something called white dwarfs, or there those are some like different kind of stellar objects, so which are, they are astrophysical objects, so they are not usual stars like sun is a, like I mean like other than sun there are other stars which are known as like white dwarfs. So or maybe neutron stars also, if you see. So these neutron stars and white dwarfs, they have within, if you see their composition, so they are like made of all fermionic matter. So it's not like how ordinary star, which is made of different gas atoms, particularly hydrogen, helium, but whatever the lighter gas atoms. But in white dwarfs and other cases, you will see they would formed out of ions, and then there would be electrons and all this. There will be like a complete fermionic soup, or like a completely fermionic I mean element. So there due to the Fermi statistics, you will have a Fermi pressure, and that Fermi pressure, you will find that that is what is balancing the stars on gravity. So, and once like in some rare events, what happens, like if the Fermi pressure becomes a bit too high, then it will explode into something known as supernova explosions. So, so again, maybe like in just a short note, I can just highlight this, that even in fermions there are uh, unique manifestation, that is like for example, white dwarfs, or in neutron stars. So it is like the the self gravity stars are balanced by Fermi pressure. Fermi pressure. So this is important due to the fermionic mechanism, due to the fermionic statistical laws, the fermionic laws that we have come through discussing here. So that leads to some specific, I mean, contribution to the pressure of the complete object. And so, and that Fermi pressure is actually balancing the star's gravity. So that is very, I mean, it's not quite conventional you will find in any other star like Sun. So, and at rare events, this Fermi pressure can overcome star's gravity and can lead to supernova explosions. So all these things, like this is so all these phenomena that we have seen, these are quantum phenomena, and how bigger they become, like how uh, their significance become important when we talk about classical objects or when we talk about objects like white dwarfs uh, or the one which we just discussed about, like something like super fluid, helium superfluid, like in Bose-Einstein condensation, you have um, helium superfluid, which has like zero viscosity, which has zero viscosity. So these are like manifestations of quantum laws. Uh, so that is what all these things you are seeing. Like I mean, so deep down underlying like principles are the ones that which we have just gone through. So it is very strange to think how they manifest at the level that we are seeing, but this is what happens. Yeah. So maybe we are almost done for today. So it's already time. It's already where I mean up with the time as well. So we can discuss again if there is any other doubt or some other issues that you are facing so far. So so already like I mean this is week 3. You are going towards your halfway of this course, which will be a week 4. I think week 4 is already also out. I mean, your lectures are there, so hopefully you are going through them, and yeah, we can discuss it, any queries you have, and you can join again this meeting, and we can discuss if there is any other problem you are having. So yeah, if there is no question, so we can stop here. Okay, so we can stop here.